So, you know that I'm not an observer originally, but in the last years it was very hard to survive without talking to observers of exoplanets. But I will try to give you my ideas on what to think of what we have learned on exoplanets, other than it's exciting to discover planets. So, what did CoRoT, or what do CoRoT and Kepler tell us about planets? So you remember that the first transit detected ever was detected in 1631 in Paris, and this transit was predicted by Johannes Kepler, and it was to prove that for the first time in history planetary ephemeris were good, because essentially through all of history nobody ever knew where planet Mercury was. Ptolemy's ephemeris were off by 20 degrees or 30 degrees. Kepler made the ephemeris of Mercury to be more accurate than the diameter of the Sun, so it was logic that the transit could be calculated, and indeed a transit was expected, and Gassendi found the first transit of a terrestrial planet ever observed in the universe. And yeah, you know that on rare occasions you also see the transit of Venus, and this is the transit of Venus from 2004 with my favorite telescope. It's a hole in the trees. Actually, it's not even a hole. It's the light falling through between the trees, and it reminds us of an important thing. The black dot, which is Venus, takes out the light a terrestrial planet takes out of a star, and that is the light that drives all life on Earth and probably on other planets. And it's a small amount which makes the things tricky. The signal is 2 times 10 to the minus 4 for an Earth-sized planet, and the solar-like stars. So you had to go to space to detect the next transit of a terrestrial planet. This was not in 2004, but in 2004 with the transit of Venus, I said to myself, the next transit will be outside the solar system. The next transit of a terrestrial planet will be outside the solar system. And fortunately, we had a satellite to do it, and this is the detection of the CoRoT satellite on the left in a rendering compared to the transit of Venus from 2004 in an image. And the rendering is made from the CoRoT measurements, including the spot. And this was the first planet ever detected, a terrestrial planet outside the solar system. So, you know that there was a unique opportunity with the double transits of Venus in 2008 and 2012. So to celebrate, I took the opportunity to go for a double transit of Venus. You know, very few people on the planet ever have seen a complete transit of Venus. And even more rare is it to see the double. So I had to go to New Zealand, and you see in the background you see the northern tip of the northern island of New Zealand, and from this island you could see the second transit of Venus also to full length. So these were the transits of small terrestrial planets which are close to my heart, but what was not so fortunate, it's a big adventure, but exoplanet discoveries have been confusing throughout the discovery thing. First, I should remind you that the first planets were discovered in 1992 in orbit around the pulsar, not a place for a good planet to be. And surprises continued. So you have I have my favorite list of surprises, and I want to just to give you the lower surprise. If you follow what is a planet in the literature, it even gets even more confusing. I mean, you know the story with Pluto, of course. Everybody knows the story of Pluto with the new definition, the Prague definition. But if you look through my listing, the mass limit of a planet, the upper mass limit of a planet has made quite a considerable evolution. with 1 Jupiter mass in 1995, the maximum mass for a good planet to have. And the most recent definition adopted by the Extrasolar Planets Encyclopedia is now 60 Jupiter masses for an argument of Hatzis and Rauer. And that's not the only surprise. This is a disk that should not exist. Yeah? This is a detection of ALMA, the Atacama Large Millimeter Array, finally good enough to resolve disks. You see the detection of ALMA on the left, and that's a sketch of the solar system on the right. Finally, the Atacama Large Millimeter Array could detect images of a size comparable to the solar system. Because before ALMA, the disks you have seen were like 10 times the solar system, 100 times the solar system. Now we have a disk since 2014, but there's a problem. There's a problem. This disk shouldn't have these structures, because these structures are most likely for mature planets, and this star is not even a good star. It's not a main sequence. It's not a main sequence star. It's not a pre-main sequence star. It's not even a T Tauri star. Yeah? It's a very early phenomenon, and still has this very mature planetary system that should not exist on this scale in this age, which is probably of the order of 1 million years. Just to show you that we have to rethink planet formation from scratch here. You have the so-called goosebumps in the Rosetta mission's comets, and you see these strange structures, and the comet is made of these structures that nobody knew would exist, but they apparently are the building blocks of things that fly around in the solar system. So to cut these stories at some point, you have heard of Proxima's planet. This is, so to say, a good planet, but hard to find, because one thing we have to keep in mind now, in particular because of this discovery, is that for exoplanets, the stars are now the limit, because we are not continuing to find exoplanets in the frequency we like, because the stars make problems. And this is an example, a unique piece of work where the problems of the star have been solved. There was searches for planets on Proxima Centauri since very early on, since the 90s, but only because the problems of the stars, it's an M star which is never well behaved, have been overcome. This nice detection could have been made, which is now a really small planet in orbit around the nearest stars. And this is to go into the red extreme even further. There is a detection of a 1.4 Earth radii planet, and this was from a project called M-Earth, designed to detect an Earth mass. It's just that the planet did not behave well, and recently when people were successful to measure the mass, it turned out it's 7 M-Earth. Because again, there's another not well-behaved planet out there, because nature is just too diverse. And if you believe a 99% safety, that is the most recent addition to the best area, a 3.2 Earth mass companion of Barnard star. So, how should we understand that? And that's now the proposal I want to make, a journey. I want to take you a short journey of 15 minutes or so. How should we understand, how should we do it, and how can we do it fast? Because there's a new discovery every year, and a new confusing discovery for our understanding of planets usually. So this is my suggestion and the motivation why you should follow on my thinking. You should follow my thinking. Yeah? The contemporary planet formation theory and our understanding of planets has to go with the following facts. We have the unknown the unknown, if you like, Rumsfeld, the unknown is there. We have to be very clear that we have not enough information to really think well about planets in our galaxy. There is a large component of randomness, and there is chaos, literally the chaos, weak and strong in the planetary systems. So we have to live with that chaos and still make something like a general theory of planets that can connect actually simple physical principles to the diversity that we find on the sky. So, and a key feature any modern theory of planet formation and planetary structure must have is it must be probabilistic in nature, because we have understood one thing: there is diversity with planets. So there is not such a thing like the main sequence is for the stars. And on the main sequence, we essentially have one temperature, one mass. There will be no such thing for planets, because if we look in the solar system, we clearly see there is diversity with planets. So, why should we do this exercise? And I let you, the people who might be more interested, can get a few hints here. Why should it be successful? Well, my basic argument is, in the end, we were successful with the theory of stellar structure to understand the stars, when the observers got it all wrong, because the first idea before stellar structure and evolution became mature was that a star starts as an O star and ends as an M star, which is not what we think now. So we need to have this theoretical approach. So let me try to convince you to rethink what you know about planets. So we first solve an idealized problem completely. A simple problem that never exists but can be mathematically done. So I invite you to the artificial place of isothermal planets. And if you are ready to think about isothermal planets, and you believe my students, you can know everything about these isothermal planets. It gives you the diversity of the isothermal planets, the masses, the densities. It's just that there is no isothermal planet on the sky. That's the difficulty. But it helps, yeah? And in particular, the concept is fruitful because you can determine a characteristic mass of planets just from physical principles, from fundamental physical constants, plus the mass of the host star. And this is this mass that you find. So it gives a characteristic mass for planets based on physics and the mass of the host star. So you can understand planets a bit, yeah? Isothermal planets. But like there is no isothermal star, there is no isothermal planet, but I show this to motivate you that it's interesting to think about it, because you learn something. So for CoRoT, we build a theory that removes the isothermality, and you can make probabilistic predictions. This is a probability density of planets as a function of mass, and you can study this for various stellar masses, big stars, small stars, old stars, young stars, and we actually we put out a prediction before the launch of CoRoT, and it served for CoRoT to guide the discovery process that I will show you in a moment. So CoRoT, the first planet hunter from space, and the theory contributed to help make the discoveries in a more strategic way, in a more orderly way. So why should this work? This is the star compass of the Carolinian Islands. You know that in the people of Polynesia, they navigated the Pacific without instruments. You know, the Pacific is mostly water, and you have only very few islands. You have to hit the islands, and it is only possible if you have a compass, a star compass in that case, that guides you. And for understanding the planet diversity, I think we also need such a star compass. We need a strong theory to understand the diversity. Otherwise, there will not be progress, except for finding another and another and another planet. So, here's an example from the CoRoT discoveries. Is CoRoT and the nature of planethood, and it shows you what is the different difficulty at the moment. You have on the abscissa, the x-axis, you have a logarithmic time in gigayears. So 10 to the 0 is a gigayear. And the red area, the reddish area, and the shaded area, that is what CoRoT has measured. It has measured a constraint for the age in blue, and a constraint for the mass, I think it's the mass, for the density, mass and radius, which is 1 sigma and 3 sigma in red and pink and pink. So you see, if you compare with the models that are behind, you see it doesn't give you a lot of constraints. Everything is possible. And of course the problem is that the error bars are so large for the density. So, okay, we can constrain planets, planetary evolution, planetary structure, in that case with statistical theory, but the observation results are not good enough. And that's not only true for CoRoT, it's even more true for Kepler, because the Kepler stars are fainter than CoRoT stars, and therefore less constraints. So, what did we find with CoRoT 7, the transit I've shown you? And this gives a few constraints. You know there's a high density planet, you know there are terrestrial planets, we have determined with CoRoT the masses for all the planets, and the Kepler people have determined the masses for a few of their planets. In the end, it's the same number of CoRoT planets and Kepler planets with good densities, which I will show in a moment. But you can constrain general things about planet formation. Yes, the planetesimal process, it happens everywhere. It can even make a 7 Earth mass planet in a very short orbit. But there is little quantitative information. Maybe the best progress from my opinion for the theory of planet formation is this one from CoRoT, and it's CoRoT 9b. This is a Jupiter in a 100-day orbit. This is a detection that you can only make from space, and because the star was big enough, was bright enough, because CoRoT stars are brighter than Kepler stars, the mass could also be measured. So for the first time, there was an indication that the theory is not totally wrong. If a Jupiter is far enough from the star, it has a good radius. But that is about what I would say, what is there in terms of quantitative theory comparison and planet formation and planetary discoveries. So, how does the situation look now if you put CoRoT and Kepler planets together? This is from the Plato mission, so to say, concept book. The diagram of the semi-major axis of the planets logarithmically, and the mass or the minimum mass of the planets for the planets that were known at that point in time. So you see the diagram looks pretty full. There's a lot of radial velocity data in cyan, a lot of transit discoveries, and so on. And you even see the solar system below on the right, yeah, with the images of the planets indicating these values. So yeah, we have lots of planets. It's a good news. Okay. So now let's do the same thing, but we ask for how many of the planets do we have extra information, except that they exist. For how many do we have densities? And the density of a planet is a key information, as we know from the solar system. That's the same diagram for the planets where we have densities. And this has not changed since it has been made. So you see it's fewer now. And now let's ask the question, okay, in the solar system, we don't have a planet inside of Mercury. So let's look at the planets that we know, where we know the density with periods, with orbital periods of less than 50 days. And that is what is left of our knowledge about the extrasolar planets. So you see, we only see the tip of the iceberg, and we don't have a lot to say about planets like in the solar system yet. So we need to continue with the discovery. Let me give you a second perspective. This is by the theoreticians, so to say, of the Kepler mission. They have summarized what they could find out in a review after most of the Kepler candidates were checked, so they were hoping to get a consistent pictures, and because they didn't have masses usually, they were estimating the masses and came up with this view as a proposal for the understanding of planets. Yeah? And there you have the various groups they proposed. There are eccentric giants, which is one proposed group. There are ungiants, there are hot Jupiters, and there are small things, essentially. So this is their proposal, but that is not enough for me. I think we have to go beyond this. But it is what we have learned from these two spacecraft. And as it has been already emphasized already, the next transit mission is flying the TESS spacecraft, which is a low-budget, quick version of Plato, the ESA mission, with a similar design. And these missions will bridge the gap to the solar system and will supply reliable information about planets like in our solar system, so we will only then see what is out there in comparison to the solar system. So I'll give you a quick outlook what will happen when we go from CoRoT to Plato. This is, so to say, the cave, Plato's cave, where you have the prisoners, they only see the shadows, and you know that with the transits, you also only see the shadows. So to make a good planet, you need the extra information, which will bring the knowledge about the understanding of the planet and formation, planetary structure. So we need this extra information. So Plato, the mission, will hopefully lead astrophysics and also the understanding of planets out of the cave by emphasizing the extra information. Yeah? A transit is not enough. It just gives you a shadow. The information comes once you measure the mass, once you know the star, once you determine the ages. That is when the planet is put in context. And I'll to give you a preview of what Plato will do, which TESS cannot do, because it's not optimized for that. TESS will give a practicing ground for short period planets, but it's not equipped with the astrophysical, with the tools to get the astrophysical information that is necessary to investigate the star in detail, and that will make the difference. So what is the difference from Plato? This gives you the CoRoT result for another CoRoT planet. And again, you have the logarithmic HS and the density in the vertical axis. You see a lot of lines. And then you see two ages, which are the age constrained by CoRoT, given in blue. And then the 1, 2, and 3 sigma limits for the density as actually determined by CoRoT. This is a work by the CoRoT team. And now if I improve the accuracy of the measurement according to the Plato specification, you see the difference that Plato will bring. Yeah? So that is what the extra mission does. It gives you an age and a density to a quality that we have had in the solar system before the space exploration started, because investigation of the solar system starts with space exploration. So, what will the Plato mission, which is the big transit mission, that will search a large fraction of the sky for planets with orbital periods until the period of our own planet, so 1 year orbital period. What can it bring to planet formation? It returns to the home zone, so we will find planets that we compare to the solar system, and we can, because we have information like the density, the age of the star, and also the age of the system and the age of the planetary system, we can do comparative planetology with the solar system and the exoplanet system. So that gives then, hopefully, the data to understand what we are seeing on the sky. Whether to see whether our system fits in well, or whether our system is an odd coincidence. And to show, and a framework for understanding this, I will show you, to finish up the theory of planetary diversity, in an example inspired by the Hertzsprung-Russell diagram of the planets. So, I'll show you the CoRoT planets in two ways. The CoRoT planets, because it's the most homogeneous system. It's not the biggest sample, but all the CoRoT discoveries have been followed up by the team, and the team has measured the masses, has measured the star, analyzed the star, and therefore we have a very consistent knowledge for the entire set of planets. Not as many as those that we have in the Kepler sample where we have published radio, right? But the number of densities that were determined, the number of planetary densities that were determined are the same or very similar to the number of planetary densities that were determined from the Kepler mission. Again, the problem is that the Kepler stars are fainter than the CoRoT stars, so the masses could not be measured with existing radial velocity facilities from the ground. So, let's look at the mass radius probabilistic diagram. So, first I rearrange the observations. So now you have the logarithm of the mass, or actually a logarithmic scale of mass, which reaches from a 10 to the 3rd mass on the left to 10 to the 3rd mass, 10 to the 4th Earth masses on the right. So almost brown dwarf or substellar masses, and you see all the limits of a planet that are discussed in the literature. And then you have the planetary radius in Jupiter radii on the ordinate. And that is the diagram that will be with us for the next decades, I think. Yeah? It's the mass versus radius diagram of planets. And depending on the nature of the planet and its evolution, it will move around in this diagram. And that is the CoRoT determinations measured and put in. And because there are measurement uncertainties, it has a probability density for every planet. So the low one is CoRoT 7 again. Yeah? The low mass, low radius is CoRoT 7 again. And you see it's not a random position in this diagram. There are some locations that are preferred. Yeah? So now we do the same thing from the theory that I've just flashed at you. I've shown you a little bit of the isothermal part of the theory, but not much more. But it's a theory which is very analogous to the theory of stellar structure and stellar evolution. And now I'll show you the theoretical statistics, but for a system as CoRoT would see it. So with the observational bias that we have heard in the first talk, as it was actually found out by the measurements of the CoRoT team. So this is the theory plus what could be detected. So you see, it's also not a random distribution. There are some places with a high probability that there is a planet with that properties. These are the red parts. and some where there's a low probability to have a planet with that respective properties, and that's blue. And that is the same thing, essentially, as you know very well from the Hertzsprung-Russell diagram, but now done for planet. And to give you an idea how well the theory might behave, you can go back and forth. So, well, this could be right. It's just not enough planets, to be sure. So, I think we'll find a lot more surprises, but most important what we need is a lot more planets, and in particular a lot more planets well measured, with well measured stars, and with periods that we can relate to our solar system. And for that, I think Plato will be the mission. And as we heard, TESS is a similar instrument, is already flying. So what I would like to call you to participate, and that's probably the reason why I'm here, that we will, together with the exoplanet transit database and the Tresca project and your president, will call to test the Plato procedures, the Plato citizen science procedures, to confirm Plato candidates with real deal test candidates. You know, Plato is a return to the bright stars for one single reason. The astronomical infrastructure on the ground, the existing infrastructure of 8-meter telescope and even 30-meter telescope, is not good enough to study planets at stars like CoRoT and Kepler found, because they are too faint. So we need to return to the bright stars, and the first instrument in the sky that has returned to the bright stars to search for planets is TESS. So we'll use their candidates to build an instrument which I actually am responsible to construct, that will help the amateur astronomers, or I prefer to call them the non-government astronomers, to help participating in the follow-up observations, in the confirmation of the planet candidates for the Plato mission, because one thing is clear already. The sky is full with planets, and therefore it will be a lot of work, and only with your help we have some chance to do that, and we can start next January with practicing. And I invite you to practice. We will announce it on the ETD, and you, with your small telescope, can participate in the effort, as we have already heard. Okay, thank you.